We're going to do an anti-Markovnikov addition of HBr to an alkene at this point in time. So I'm going to use the exact same one we had previously. And again, it doesn't matter if you use wedges or dashes, since there is an intermediate formed in this case, which will be a radical. And so you're going to lose the syn and anti characteristics of this reaction. This particular type of reaction only works with HBr. It doesn't work with HI, HCl, or HF for a variety of reasons. Now, nobody knows entirely why that is, but it only works with HBr, and you must have a peroxide present to initiate this reaction, and you're going to do this with UV light. This is a free radical process. And it is still, just like we saw with the Markovnikov reaction, about making the most stable intermediate. So even though this does an anti-Markovnikov addition, it makes sense if you know who adds first. In this reaction, it's the bromide that is going to add first, and then the hydrogen. In the Markovnikov addition, it's the proton that adds first, then the bromide. So you're still trying to make the most stable intermediate. It's just that this reaction proceeds by a radical process instead of a process that involves a carbocation intermediate. So the first step of this reaction is called initiation. And in this step, we're going to use the UV light to break apart the peroxide bond. Now those R groups can be hydrogens or other carbon chains. It really doesn't matter. The point is you will have this peroxide and you're going to hit it up with a specific wavelength of UV light. What's going to happen here is that you're going to break apart the completely covalent oxygen bond here. Because it's completely covalent, these electrons in this oxygen bond share electrons completely equally. And so if the bond is broken, each atom gets one electron. And to show that, we use single-headed arrows so that we know that one electron is moving, not two. And so as a result of this first step, you get an RO radical, and you would get two of them. Now, oxygen, like any other normal nonmetal, likes to have an octet of electrons. And right now it has 7. So they could choose to come right back together, which is an option, but that's not productive, or they could do something else. And what they're going to do in the second step of this initiation reaction is they're going to react with the HBr that is in the solution. Now, I have really stupid analogies, as you've learned in class, and I call this the gradient robber because we're going to have a radical propagate a radical. So it's propaganda, I call it, radical propaganda. You're spreading the radical around. So if you have a radical, you got to make a radical. This oxygen needs an electron. It needs just one electron to maintain an octet. So when it breaks apart this HBr bond, which is heterolytic, it doesn't want to take just an H+. That wouldn't help it any. It needs an electron. So it's going to take the hydrogen and its electron because it needs the electron. And it doesn't want to take the hydrogen with both electrons. It doesn't want a hydride either. That would be too many electrons. It just needs one. And so it's going to break apart this HBr bond homolytically in order for the ROH bond to be formed here. And it goes after the hydrogen because it's a smaller atom. It's easier to remove that smaller atom than it is the larger one. Okay, but as a result of that, you're going to make bromide radical, which we have seen previously in class. But this is how we're going to initiate the reaction to form that bromide. It's not even bromide, but it's a bromine radical, bromine atom. So the next step is propagation. So again, this is the radical propagation. You got to spread your propaganda. So if you have a radical, you got to make a radical. If you don't end up with a radical on both sides of the arrow, so you start with one and you make one, you did something seriously wrong. And you need to think about that. But you start out with this bromine atom, or you can call it bromine radical. And you need another electron. Now, you can get this from a couple of places. You can get it from HBr, but that means if you stole the hydrogen atom from HBr, you made another bromine radical, and that's not productive. So we aren't going to talk about that option. The only other option you have is the alkene. Okay. Now, alkenes have a couple of different types of bonds. You have sigma bonds, and you have pi bonds. Now, I am hoping you remember way back when we talked about hybridization, that pi bonds are higher in energy than sigma bonds, meaning pi bonds are weaker than sigma bonds. They're easier to break. So if you're going to break a bond, you're not going to want to break a sigma bond and take a hydrogen because those bonds are higher in energy. It's harder to break one. It's much easier to break the pi bond. It's a weaker bond. So that's what bromine is going to do. It's not going to go after a hydrogen here, like we saw with the alkanes. The reason it worked that way with alkanes is because there wasn't a double bond. But here there is a double bond. So you're going to go for the double bond. It's a weaker bond. So this bromide, or bromine, sorry, is going to come in here with its electron, and it's going to add to this double bond. And as it does so, you want to break it and make the most stable intermediate possible, which means I'd rather have a secondary radical than a primary radical. So after addition, you're going to end up here with this secondary radical. So it's the bromide that adds first in this reaction, and this is the product of that first step. So notice, initially you started off with a radical, you ended up with a radical. That's why it's propagation step. If you didn't end up with a radical, you did something wrong. Now, we did not make ourselves completely happy here. We still have a radical, but we made the more stable radical. That's why it's on the secondary carbon instead of on the primary carbon. The bromine added to the primary carbon to make the more stable intermediate. This is very similar to what we saw with the Markovnikov reaction, except there you added a proton first to make a carbocation. Here we added a bromine atom first to make a secondary radical. The radical needs to satisfy itself somehow, and so we'll bring in some more HBr because it's abundant in solution. There's more than one. I have a lot of students that seem to think once you've used it, you can't use it again. There's lots of it. But I need somebody. Now, hydrogen's smaller than bromine. So I'm going to take the hydrogen atom and make a bond to this carbon. Again, I need one electron. I don't need none. I don't need two. I just need one. So this electron will pair up with one of the electrons from this HBr bond and take the hydrogen with it. The other electron just has to go to the bromine. So again, remember, we're starting with a radical. You're going to have to make a radical, and I'll show that radical here in a minute. You made another bromine radical, which is wonderful, so you can use it and go all the way to the beginning again and start all over. Okay, so we had a radical and we made one. Now, at this step, the one that we just did, I find that a lot of students seem to want to try to do this some other way and not make another radical. They'll try about anything. They might just try another bromine in the solution or somehow pull out of their hat a hydrogen atom. You can't do that. It does need to be the HBr that you use this with to make this anti-Markovnikov addition to make this alkyl halide here that you see. Now, this other bromine atom, it does this process again, and it keeps propagating itself and going on and on and on. Eventually, though, you will get to a termination step. The termination step is a step in which two radicals come together and you stop the propagation. I could care less what two radicals you bring together. It does not matter. I like to keep it simple. If it's a radical that was formed during the course of the reaction, you can use it. Keep it simple. That's one that works. You could have two RO radicals coming together to remake the peroxide. You could have two carbon radicals coming together to make some long carbon chain. It doesn't matter. These are going to be minor products in the solution, but this is how the radical reaction would finally be terminated.